Okay, let's talk about the maximum height. Okay, there are two different ways you could obtain the maximum height. I'm going to draw the picture again. I'm going to copy paste this thing. Yeah, we will do that. That's more efficient. Okay, so this is the thing we were discussing about, and now I am worried about this maximum height up here. Let's call this point C. Okay, if you really think about this, you would understand that the maximum height, at the maximum height, if you think about the speed of the particle, you have to understand that it's purely horizontal, because that's why it didn't go up further from that, because the vertical speed reduced on the way and became so small and eventually becomes zero. So after that, the speed is going to simply reverse. The vertical speed is going to simply reverse and increase, and at the moment it hit the ground, since we are assuming there are no other forces on it, it would be exactly equal to this u sine theta, but in the opposite direction. But throughout the motion, if you remember the acceleration of this being downward and is equal to g, throughout the motion there's no horizontal acceleration, because as you know, if you have a vector, there's no perpendicular component. The component it has, or the effect it has on the perpendicular direction, in the perpendicular direction, is zero, because if you even try to resolve it, it would come as that vector cos 90, and the cos 90 is going to be 0. So this is kind of g cos 90 in this way, and it's equal to 0 because cos 90 is 0. Now, keeping that in mind, you have to understand now the horizontal velocity it has is always going to be u cos theta, because at the initial point we have u cos theta, so it's going to be u cos theta throughout the motion, irrespective of where you are. So keeping that in mind, I can apply equations from A to C. Okay, remember, I'm not going to apply just for the motion. I'm going to say from which situation to which situation I'm going to apply this. So A to C, applying what equation should I choose? Think. Stop the video for a while. Think, what equation should I use? I'm going to just go through it without giving you time, because you have a pause button. Okay, don't forget it. So when it comes to thinking parts, just stop the video and start thinking. Okay, I'm going to apply v squared equals u squared plus 2as upward. So since I'm applying upward, I'm going to apply all these vector quantities in upward direction. So my v is my final velocity, and upward it's going to be 0. My initial speed upward, u sine theta squared. 2, acceleration upward is minus g, and displacement upward going from A to C, and upward displacement is going to be h. If you just consider the motion from A to C, the displacement is going to be this much, but we are not considering that. We are considering upward. So even if you think this is the displacement, we need the vertical component of it, which is exactly going to be h. So upon simplification here, we get h is equal to u squared sine squared theta over 2g, which is the next result we were talking about. And also keep in mind that the sine theta whole thing squared is written as sine squared theta, not as sine theta squared. So that's simply notation in maths. We prefer this thing over this thing. That's it. Now, I was talking about another method to do this. The other method is using conservation of energy, conservation of mechanical energy. So if we write conservation of mechanical energy using conservation of mechanical energy for the motion from A to C. If you think about it, I'll redraw a part of the diagram. So we threw it with u, and this is the maximum point, where this point is A, this point is C, and we know the horizontal speed is u cos theta. If we understood that earlier argument I made, there being no horizontal acceleration. The vertical acceleration is there, so the vertical velocity was changed throughout the motion, but it returned to zero, vertical velocity being zero at that top point. And this height is what we are looking for, and this is our horizontal level. I'm going to consider a zero level for gravitational potential energy, not energy, gravitational potential zero level. So that means the gravitational potential energy for a mass being in that level is going to be zero. So we are throwing a certain mass. So this is the mass that we are throwing. So I'm going to simply write at A and C the total mechanical energy of the system. Actually, the total mechanical energy of the mass M. So if I start at A, I have a kinetic energy half mu squared, and since I consider the gravitational potential zero level being in the horizontal level of A, my gravitational potential energy is zero. If you think about it, is there any elastic potential energies? No, there was no change in the shape of the object or any such scenario, so there is no elastic potential energy, so we don't even mention it. Now coming to C, I have a kinetic energy of half m u sine theta whole thing, u cos theta whole thing squared. And at that point, I have a gravitational potential energy of mgh, because I'm writing from this level up to there, there's a height of capital H. Now it doesn't seem to have given us the answer straight away, but let's do the simplification and see. So we can clearly see the m cancels off, so that's weird. Although we are throwing the mass m, earlier we didn't see that, we didn't have a mass in it, so we were not worried about it. But this one needed the mass to write down, but although it needed the mass does not dictate what the value of capital H is. That's really interesting. Now if I simplify, I can take a half u squared out. So here I'm left with the 1, and this part is going to be cos squared theta. Coming to this side, it's going to be minus cos squared theta, and this side is going to be gh. We need a little bit of trigonometry to move on from here. If you remember, 1 minus cos squared theta is sine squared theta, as sine squared theta plus cos squared theta is one of the identities in trigonometry, which is very important. It's kind of a trigonometric equivalent of trigonometric equivalent of Pythagoras' identity. Okay, it's basically the Pythagoras identity in terms of trigonometric terms. So if I use that result here, I get half u squared sine squared theta equals gh, and which gives us our answer to h as u squared sine squared theta over 2g. Okay, so this is that result, also using the conservation of mechanical energy, and we first did using equations of motion, which did not involve any masses. We simply wrote equations of motion because this is constant acceleration scenario. Then we also saw, since there's no energy losses associated with this motion, because we only assumed that the gravitational forces are the only forces that acts on the object, and in that case gravitational fields, so gravitational force fields are, we say, conservative fields. So when you travel through a path, the potential energy difference does not depend on the path, things like that are there, being a conservative field. So we can pretty much apply the conservation of mechanical energy, and we got this result. So this is it for the maximum height. Then next we will talk about the horizontal range and its application. Wait a minute. So we didn't talk about the things that affect h. So if you look at it, h, you can see it's proportional to u squared. Earlier the time was proportional to u, directly proportional to u. That means if you double the speed, the time it takes, the flight time it takes, doubled. But in this case, if you double the speed, initial speed, your height will become 4 times, because it will become square of it. So you are expecting a much larger height, but only the double the speed, the 4 times the height if you double the speed. Oh, I think I said it completely wrong. If you double the speed, you're expecting 2 times the flight time and 4 times the maximum height. Okay, and also h is proportional to, again, see, it's not sine theta, sine square theta. H is directly proportional to sine square theta. But again, you can grab, since we are like discussing about theta being between 0 and 90, we can also include the equal to 90 scenario. It's not an inclined projectile, it's a vertical motion under gravity, vertically. In this case, we can see if theta increases, it should increase at a much larger rate now. But how the theta increases, you can't say like theta doubled, I mean h is made 4 times. It's not going to work like that. But theta increasing would increase h, definitely. And again, we see the inversely proportional nature of g. So higher the g, smaller the height, lesser the g, larger the height. Again, this adds up to that illusion of like people walking on moon or jumping on moon, taking much longer time to come down and traveling a much larger height. That's why we kind of see them as jumping. They're simply like trying to run or walk, but well, like we see a larger maximum height, so we think they're always jumping. Maybe they're jumping, I don't know. We have to ask them. So this is it. And okay, so this is not it. So I can consider the theta equals 90 scenario, and in that case the h is going to be the maximum value. H max is going to be u squared sine squared 90 over 2g, which is going to simplify to u squared into just 1 squared over 2g, or u squared over 2g. So this is the maximum height it will take that comes at an angle theta. So for a scenario, you're basically throwing the particle vertically upward. In this case, this maximum height, this height, let's get rid of that maximum at the 90-degree scenario, let's call it. So this is going to be u squared over 2g. So what I'm basically showing you is that you don't have to remember the vertical formulas, just the vertical formulas. You could simply grab them from here. Okay, now that's it for this video, and we will discuss about the horizontal range in next video and things associated with that. Okay.